Welcome to the WP6 demo. In this video, we will show how itwinai, namely the component for AI workflows, integrates with federated computing infrastructure, workflow execution, quality assessment, infrastructure provisioning, and to demonstrate how these components integrate together, we will show how the CERN use case, namely the interTwin use case for particle detector simulation using 3D GAN models, is deployed accessing infrastructure resources through itwinai. Here we can see on the right-hand side of the screen how itwinai allows to represent AI workflows in a modular and reproducible way through configuration files. Configuration files allow to break down AI workflows into steps. So in this configuration file that we can see here, we have two steps. First is the preprocessing and data loading. Second is the actual machine learning training. And this allows the use case to break down their code, which is represented on the left-hand side of the screen. And the configuration file will provide a unified entry point from which the whole AI workflow can be configured and modified in successive executions. Let's now see how the quality component integrates to provide an assessment of the quality of the software that the use case is developing. So let's assume we change something in our code, for instance, a parameter in the configuration file, and we push the changes to our repository. This will trigger some automatic GitHub actions, such as the linter and others, but the most important one is the SQAaaS. When the analysis is complete, we can access the report from the README file. And here we can inspect the details of the analysis performed on our software. We can earn some badges if the quality is good enough, and we can inspect further details of the quality assessment of our code. For instance, the code accessibility, documentation, licensing, security, code style, versioning, and code metadata. The next step that the use case developer will perform is to train the model on his local laptop to verify that everything is working well. So here we can see how we can train a neural network in a local virtual environment on the local laptop of the experimenter. And when the training is complete, the experimenter can access the results present on the MLflow component. From here, the experimenter can analyze the effect of the parameters on the metrics and can compare the parameters to understand which ones influence more the results in order to tune the AI workflows and obtain the best performance. Moreover, MLflow gives the possibility to the use case developer to further inspect the details of each execution run of an AI workflow. For instance, inspecting the evolution of the metrics over time, comparing them and visualizing them in different ways. But also MLflow provides a so-called models registry in which pre-trained models can be stored and versioned, and the use case developer can manage them from a unified portal. Let's see now how we can provision cloud resources to scale our local workflow to cloud and HPC infrastructure.
We are going to select the template to deploy, in particular the Kubeflow one. Then we have to parameterize the template to adapt to our needs. First, we set a descriptive name, and then we can set the features of the front-end node. In the second tab, we can adjust the number of working nodes in our cluster and their features. We can also specify a set of parameters of the Kubernetes cluster. And finally, in the Kubeflow, we can set the username and password and the version to install. Finally, we select the cloud provider, the GSC provider that we have just added, and the base image we use, in this particular case, an Ubuntu 22. And finally, click on Submit to deploy it. Then we only have to wait a bit, about 15 minutes, to have our Kubeflow instance up and running.
It is now time to scale our prototype to cloud infrastructure, and to facilitate this, the use case developer can bundle the code in a container and push it to her preferred containers registry. Now the developer can connect to the deployed Kubeflow instance to access a large number of advanced machine learning tools, for instance, Jupyter notebooks. From here, the use case developer can reuse the workflow defined in the configuration file we saw at the beginning and translate it in a simple way into a Kubeflow pipeline definition. This means reloading some steps from their name and, if necessary, overriding some fields. From the Kubeflow pipeline graphical user interface, the use case developer can monitor in real time the evolution of the execution of the pipeline he submitted. Once each step is completed, the use case developer can inspect the logs of the execution. In this example, we can see that the pipeline that we defined at the beginning of the demo is now mapped to a Kubeflow pipeline with 2 steps, composed in data loading and training.
Now I'm going to show how we use the itwinai component package inside a Docker container to train the neural network of the CERN use case on the Jülich Supercomputing Center using interLink. For this, we need to define a Kubernetes pod where we can simply add an annotation to define which hardware we want to use. Here, we want to use 4 GPUs for our training. We select the itwinai container image, which needed to be pre-staged beforehand. We state the command to execute the training as defined by our pipeline configuration file seen in the very beginning of the video. We simply select the Jülich virtual kubelet as our offloading destination, and we submit the pod to the cluster using a single command in the terminal. We see that the pod is now in the queue waiting for the training to start. We can inspect the logs and see that indeed the training has commenced using the 4 GPUs as intended.
Let's assume that the training of our model on cloud and HPC resources is concluded. We can now use it in inference mode to make predictions. To achieve so, we will use OSCAR, which in turn will access HPC resources through the interLink component for federated computing infrastructure.
Hello, my name is Estibaliz Parcero from Universitat Politècnica de València. In this part of the demo, we will show you how to use OSCAR, a data-driven serverless computing platform developed at UPV to offload computations through interLink developed at the INFN into Vega supercomputer at the ISUMA Center in Slovenia. First, we need to create an OSCAR service for the use case. Using the OSCAR command line interface, we'll apply a YAML file to create the service. We have an itwinai inference process of a 3D GAN model for particle detector simulation provided by CERN. The created YAML file specifies the Docker image that contains the use case, the shell script to be executed to perform the inference from the input data, and as a storage provider we use the cache, a distributed storage system provided by DAISY. Now that we created the OSCAR service, we are going to use itwinai, a tool developed in the UPV to define the data flow that connects the cache and OSCAR through Apache NiFi. So using itwinai, we can apply a YAML file that contains the desired data flow. In the Apache NiFi graphical interface, we can inspect the created data flow. Once we check the data flow, we can sort it, so Apache NiFi will be monitoring the cache for storage events. With the service and the data flow created, we can upload data to the cache. This activates the NiFi flow that triggers the OSCAR service that creates a job to process this data. Here in the OSCAR graphical interface, we can see the job has been created. If we inspect the logs, we can see the job has been executed. So what happened there is that the job has been offloaded to the Vega supercomputer. If we inspect the nodes, we can see there is a node called Vega new VK. This node is created by a virtual kubelet and used by interLink. so everything that is placed in this node will be offloaded to the Vega supercomputer. Now, if we inspect the pod created by our job, we see that it has been successfully assigned to the Vega node. To do that, we added some Slurm annotations and a node selector. Once the job is offloaded to Vega, the input data is downloaded by the OSCAR fast supervisor. The user script is executed, and the result is uploaded by the supervisor to the cache. Finally, we can go to the cache and download the result of the process. To conclude, we've shown you how we provide a scalable event-driven AI inference with workload offloading across cloud and HPC environments. That's it for this video demo. We hope you enjoyed it. Thank you for watching.